Hello everybody. Today topic is the basic modes of ventilation. So ventilator delivers a set volume of the gas to patient based on the volume, pressure or flow as set by operator. So we'll see physics of mechanical ventilators. A mechanical ventilator either fully or partially supports a patient work of breathing. The basic build of mechanical ventilator can be described according to input power, source of pressurized gas, drive mechanism or control circuit. So we'll see what is input power. Input power can be pneumatic, electrical and combined. Pneumatic means compressed, there will be the compressed medical gases are used as energy source. Then electrical will be AC or DC current is used to derive pistons and compressor that generate pressure. Then next is combined. That means most intensive care unit ventilator are combined with pneumatic power used to deliver the breath while electronically control pressures control the valves that regulate the characteristic of the breath. Now the source of the pressurized gas, clearly both oxygen and air are required. These may be provided via hospital central manifold supply with blender mixing them to achieve the desired oxygen concentration. Alternatively, some machines may use an oxygen cylinder alongside an air compressor, while others will have inbuilt turbine as a source of compressed air. Now, drive mechanism. This is the system used by the ventilator to convert input power into ventilatory work. There are three types like piston, bellows, and the pneumatic circuit. The most commonly used is pneumatic drive mechanism. Pneumatic drive mechanism uses the micropressor control and a proportional solenoid valve that convert electrical energy to mechanical energy. And the micropressor controls the solenoid, that is electromechanically operated valve, to open and close the valve according to the desired flow or pressure pattern. The solenoid valves are the control unit which, when electrically energized or de-energized, either shut off or allow the fluid and gas flow. The actuator takes the form of electromagnet. When energized, the electrical field builds up, which pulls the plunger against the action of the spring. When de-energized, the plunger is returned to its original position by the spring action. Now the next is control circuit, the system that controls the ventilator drive mechanism and the inspiratory and expiratory valve is the control circuit. The control circuit can be classified as open or closed. We'll see what is open loop. Open loop control circuit achieves the set desired output without responding to changing conditions such as circuit leak. Open control circuits are not controlled by the microprocessors. Now the closed loop control circuit adjusts the input to match the desired set output as a result of ventilator measuring flow, pressure or volume, allowing compensation for changing conditions. Control circuit can be classified based on their underlying mechanism like mechanical, pneumatic, electronic or fluid. Mechanical control circuit are open loop circuit used in the older mechanical ventilator that uses levers and pulleys to control the drive mechanism. Pneumatic control circuit uses the valve, nozzles, ejectors and diaphragm to control the drive mechanism. Now, electronic control circuit uses the resistors, diodes, and circuit and microprocessors to control the drive mechanism of the ventilator. And fluidic control circuit works similarly to electronic control circuit, but control the direction of the gas flow, perform the logic function based on the fluidic instance. Fluidics uses the fluid dynamic to perform the function otherwise controlled by the electronics. Now the next is humidification and warming. The gas at source is dry and may be cooled. In addition, the endotracheal tube bypasses the natural humidification mechanism of the nose and the pharynx. Breathing dry cold gas will lead mucociliary dysfunction and retention of circulation. So artificial humidification of inspired gas is necessary. Uh, Then the humidification can be achieved passively using standard heat and moisture exchange filters. This method is less efficient and the suitable only for short-term ventilation, as filter needs to be changed regularly to mitigate the risk of it getting blocked with secretions. This incidentally increase the risk of aerosolization and infection spread. Active water bath humidification, which pass the inspiratory gas over the heated water bath, is most efficient method of the humidification. Other methods of active humidification exist but are less commonly used. This is the schematic diagram of the heated humidifier. Now the next concept is the airway resistance. Airway resistance is the obstruction of the airflow in the airway, normally 0.5 to 2.5 centimeter of water. It is affected by the two factors, the velocity of the gas flow and the airway radius. The regarding velocity of gas flow can be turbulent and the laminar. Transition from the laminar to the turbulent flow occurs when the Reynolds number is greater than the 2000. The Reynolds number is the dimensionless number that increases with the gas flow velocity. And the turbulent gas flow results in much higher airway resistance than the laminar flow. Now the next concept is the airway resistance. Airway resistance is inversely proportional to the radius as per Huygens-Poisson equation. The small reduction in the airway resistance can lead to large increase in airway. Thus, a small reduction in airway radius can lead to large increase in airway resistance. So, according to this formula equation, the airway resistance is equal to the is inversely proportional to the fourth power of the resistance radius. It can be seen from the equation that airway resistance also varies directly with the length of airway or endotracheal tube and the viscosity of the gas. So the airway resistance can be calculated in the following way. Change in the pressure or change in volume or peak pressure and plateau pressure and flow. So change in airway resistance can be visually observed on the ventilator system using pressure volume loop display. An increase in the bowing that suggestive of increased inspiratory and expiratory flow resistance of the pressure volume loop suggests the overall increase in the airway resistance. So in this diagram, there is increased bowing of the pressure volume loop suggests the increase in the airway resistance. The bowing of the inspiratory limb may be caused by excessive inspiratory flow, and bowing of the expiratory limb may be caused by the increase in the expiratory flow resistance, such as bronchospasm. Now, the next concept is the compliance. Lung compliance is the measure of the distensibility of the lung. It is the change in the volume per change in the transpulmonary pressure, and it is calculated in the following way. Where C is the compliance, delta V is the change in volume, and delta P is the change in the transpulmonary pressure. Low compliance means lungs are stiff and non-compliant, making the lung expansion difficult and increasing the work of breathing. For example, in acute respiratory distress syndrome, high compliance means there is incomplete exhalation, airway trapping, and reduced CO2 elimination due to lack of elastic recoil in the lung. For example, emphysema. For typical lung at functional residual capacity, compliance is 200. And the typical values for the lung and thoracic cage compliance are 200. Therefore, typical values for respiratory compliance would be 100. Now the next is static compliance. This is measured when there is no gas flow in the lung and it relates to the elastic resistance of the lung and the chest. It can be represented graphically by the pressure volume graph, which shows pressure volume relationship between lung volume and intrathoracic pressure is not linear. Condition that decreases the static compliance are as follows. Acute respiratory distress syndrome, atelectasis, abdominal distension, consolidation, obesity, pleural effusion, pneumothorax, and the retained secretions. Condition causing the increase in the static compliance are emphysema, flail chest, and sternum. The dynamic compliance is measured when the airflow is present. It includes both airway resistance and the elastic resistance of the lung and the chest wall. So, by including airway resistance, it is therefore always lower than the static compliance. So this is the diagrammatic representation. If the if pressure volume curve is flat, so the lung compliance will be low, and the range is in the range of -5 to -10. The pressure volume curve is the steepest, and the small change in the transpulmonary pressure will lead to large change in the lung volume. Thus, the lung compliance will be maximum at the functional respiratory capacity. So the figure 6 shows the different courses of inspiratory and expiratory curve following the normal breath. These different courses give rise to loop, the area within which represents the amount of energy used in overcoming the restrictive force in the air. The straight line joining them represents the dynamic compliance, and the loop effect is called as hysteresis. Condition causing the decrease in the dynamic compliance are as follow: bronchospasm, kinking the endotracheal tube, and the airway obstruction. The method to measure the static and dynamic compliance is as follow: obtain the correct tidal volume, obtain plateau pressure by applying inspiratory fold, and then obtain the peak inspiratory pressure. Static compliance is calculated as tidal volume upon plateau pressure minus peak, and the dynamic compliance is calculated as tidal volume upon peak pressure minus peak. So the mechanics of the ventilator: gas flow into the lung down the trans airway pressure gradient. So the trans airway pressure is equal to airway pressure minus alveolar pressure. So this is the compliance curve in which in this graph the compliance is measured for every 5 centimeter increase in airway pressure. From zero end expiratory pressure, the airway pressure is increased in 5 centimeter increment. The corresponding change in the volume is plotted. As you can see, the change in the volume increased by every 5 centimeter of water pressure as we move in the right side of the graph, implying better compliance and the reduced work of breathing. So this is the diagram showing the lung ventilator diaphragm. The gradient can be generated via the positive and negative pressure ventilation. The negative pressure ventilation creates this pressure by applying negative pressure to the chest wall, which subsequently decreases the alveolar pressure. Positive pressure ventilation creates the pressure gradient by applying positive pressure at the airways. The lung ventilator unit, as we have seen in the previous diagram, it can be thought of as a tube with balloon at one end. So positive pressure ventilation creates the pressure gradient by applying positive pressure at the air. And the lung ventilator unit can be thought of tube with balloon at the end. So the pressure at B is equivalent to the alveolar pressure and can be determined by the volume required to inflate the alveoli divided by compliance of the alveoli plus baseline P. And the pressure at A is equivalent to the airway pressure measured by a ventilator, and it is the product of the flow and resistance added to the pressure at point B. If considering this the ideal pair of the lung, then flow, volume, and pressure are variable while resistance and the compliance are constant. The figure shows the relationship between the pressure, flow, and the volume, and by setting one, the other to become constant. It also shows that it is not possible to preset more than one variable at a time. Thus, in the volume in the flow preset mode, the pressure becomes the dependent variable, and it is important to monitor pressure to minimize the risk of barotrauma. However, it is alveolar pressure, not the airway pressure, that is important. Alveolar pressure can be determined by measuring airway pressure after end expiratory pause, as gas will distributed throughout the lung unit, thereby achieving the equilibrium. However, alveolar pressure can be higher than the measured pressure, for example, bronchospasm, if there is a gas trap. The pressure at the end of each lung insufflation is peak airway pressure that is needed to overcome resistive and the elastic forces in the lung and chest wall. The pressure in the alveoli at the end of inspiration is plateau pressure. The trigger, now the next concept is trigger. Trigger is the event that initiates each mechanical breath. And the following can be triggers. It can be time trigger, it can be pressure trigger, flow trigger, and neural assist trigger. Now we'll see what is time trigger. The time trigger means the patient initiate the breath according to the set inspiratory rate, independent of the patient effort. So for respiratory rate of 15, the each respiratory cycle lasts for 4 seconds. So the ventilator initiates a breathe on every 5th second. Now the pressure trigger, spontaneous breath effort drop the airway pressure below the set peak. When the drop reaches the set trigger pressure and the breath is initiated. Now what is the flow trigger? A spontaneous breath effort can also cause inspiratory flow of the gas that is detected by ventilator, and this initiates the inspiration. Now the next is neural assist trigger. Neurally adjusted ventilator assist is the mode where the ventilator is able to sense electrical diaphragmatic activity and is therefore initiated as assisted breath. Now the next concept is limit. The limit is the mechanism that determine how the breath is delivered to the patient rather than the factor that brings the inspiration to the end. It can be one of the following: flow limited. The fixed flow is delivered over the set time interval so that known tidal volume will be delivered to the patient. And the pressure limited means a fixed pressure is set within the fixed time interval and the volume delivered varies with patient characteristics such as lung compliance. Now the next concept is cycling. Cycling is the factor that governs the changeover from the inspiration to expiration. Inspiration ends on attaining the preset parameter, and this preset parameter can be one of the following: volume cycling or time cycling. Volume cycling means cycling occurs over the preset volume is delivered. Time cycle means cycling occurs after preset time is delivered, and this can be set directly or indirectly. Directly by setting inspiratory time, indirectly by setting the ratio of inspiration to expiration. Now the flow during pressure supported breath, the inspiratory flow increases and the decline after reaching peak inspiratory flow. Once this flow declines to preset expiratory flow rate, usually described as percentage of peak inspiratory flow rate, and cycling occurs to the expiration. Expiratory trigger sensitivity of 50%, 25%, and 10% results in cycling at 40, 20, and 8 ml per minute flow respectively. Inspiratory time and the tidal volume are inversely proportional to the expiratory trigger sensitivity. If there were to be leak in the system, cycling would not occur as the decelerating flow could be prevented from reaching the expiratory triggering sensitivity setting, resulting in prolonged inspiration. To prevent this, maximum inspiratory time can be set, which is particularly valuable in non-invasive ventilation mode where leakage is almost certain. Now the pressure cycling occurs after preset pressure is reached, and this reduces the risk of barrel. If the airway pressure exceeds the set maximum, the ventilator will cycle to expiration, regardless of tidal volume being delivered. Thus, high airway pressure may lead to the premature termination of expiration, causing degree of hyperventilation. Now, this is the diagram showing the flow cycling at 10%, 20%, and 50% of expiratory trigger sensitivity. Now, the ventilator breathe type. Ventilator delivered breath can be controller assisted. Control breath initiated by ventilator, preset volume or preset pressure. Assisted breath initiated by ventilator and assisted by the ventilator. Now we'll see what is volume control. In volume control ventilation, the same pre-specified tidal volume is delivered with each inspiratory cycle, regardless of whether the breath is time or the patient trigger. And the key provider setting include flow rate, tidal volume, respiratory rate, PEEP, and the fraction of inspired oxygen. Depending on the ventilator, the user will input either flow rate, tidal volume, or inspiratory time and tidal. In volume control ventilation, the pressure is not controlled. It is dependent variable determined by the airway resistance and lung compliance. As resistance increases and compliance worsens, the flow will remain constant and pressure will rise. The advantage of volume control ventilation include guaranteed tidal volume, stable minute ventilation, ability to specify flow rate, which could be advantageous in setting of high airway resistance. And disadvantages are injurious pressure may be generated in setting of worsening lung compliance and high resistance. So variable defining common ventilator mode. The volume control, the trigger will be time or patient initiated, control will be flow, and the cycling will be volume. And the pressure control mode, the trigger will be time or pressure initiated, control will be pressure, and the cycling will be time cycling. In pressure support ventilation, again the trigger will be pressure initiated, control will be pressure, and cycling will be flow. In pressure regulated volume control, the trigger will be time or pressure initiated, control will be by pressure, and cycling will be determined by the time. Now, in the pressure control ventilation, constant inspiratory pressure is applied throughout the inspiration, regardless of whether the ventilator or patient initiates the breath. The key provider setting includes inspiratory pressure, inspiratory time, respiratory rate, PEEP, and effect. Depending upon the ventilator, the user will input either total inspiratory pressure desired or inspiratory pressure to be applied above PEEP. In this mode, the flow and the resulting tidal volume are dependent variable and vary with changes in the airway resistance and lung compliance. Another one advantage of pressure control is that airway and the pulmonary pressure never exceed the selected inspiratory pressure. Thus, the risk of barotrauma can be minimized. Another advantage is that the patient control their inspiratory flow rate and airflow will increase in proportion to the inspiratory effort, improving patient comfort and minimizing patient ventilator dyssynchrony. So this is the volume control waveform and this is the pressure control waveform. And the disadvantage is that delivered tidal volume can be varying. As the resistance decreases, the compliance improves and the pressure may lead to excessive tidal volume. Alternatively, if resistance increase and the compliance worsen, the same pressure will generate much smaller volume, result into the poor ventilation, carbon dioxide retention, and the ventilatory failure. Now the next is pressure regulated volume control. The pressure regulated volume control is the mode of mechanical ventilation that uses adaptive target scheme of automatically adjust the inspiratory pressure to achieve specified tidal volume. So the key providers are target or tidal volume, inspiratory time, respiratory rate, PEEP, and FR2. The commonly used name for this mode is PRVC is misleading. Flow and volume are not controlled. Pressure is the control variable and flow varies with the change in airway resistance, lung compliance, and patient. So this is the graph of the pressure regulated volume control. To achieve the target tidal volume, PRVC monitors tidal volume resulting from the applied inspiratory pressure. If the tidal volume is higher than the target, applied pressure for the next breath is decreased. If it is less than the target, then the applied pressure is increased for the next. In this way, PRVC allows for the breath-by-breath pressure adjustment to achieve the desired volume in the face of changing resistance, compliance, and the patient. PRVC theoretically provides the benefit of variable flow from pressure control with guaranteed minute ventilation of volume control without requiring the user to adjust the inspiratory pressure. The disadvantage of the PRVC is the potential for patient ventilator dyssynchrony in patients with high respiratory rate. If the patient develops increased work of breathing and is generating larger tidal volume at given inspiratory pressure, the adaptive targeting scheme will continue to reduce inspiratory pressure with each subsequent breath. The result is less support from the ventilator and increase in patient work of breathing. PRVC therefore be used in patients who have stable respiratory tracts. Now evaluating respiratory mechanics in the different modes, the change in resistance and compliance manifests differently with different mode of the mechanical ventilation. In volume control ventilation, increased resistance and the worsening compliance or both result in increase in pressure. The two scenarios can be differentiated by comparing maximum pressure during inspiration or peak pressure and pressure required to keep lung inflated once the inspiratory flow had stopped and plateau pressure. The peak pressure is simply highest pressure observed on the pressure versus time displayed on the ventilator. The plateau pressure is measured by performing inspiratory hold maneuver, where the ventilator seizes the airflow at the end of inspiration and measures the pressure in the respiratory segment. Because the lungs are fully inflated and exhalation has not yet occurred, this represents the total pressure in the lung, inclusive of PEEP at specified volume. The larger difference between peak and plateau pressure will be observed when the limiting factor to gas delivery is resistance to the air. The small differential will occur when limiting factor is compliance of the respiratory system. The pressure control and pressure support. In pressure control and pressure support ventilation, inspiratory pressure is fixed at the value set by the operator, and therefore high resistance and worsening compliance will both cause or decrease in the observed tidal volume without way to reliably differentiate between these two scenarios. An adaptive mode PRVC varies the inspiratory pressure based on the mechanics of the respiratory system. Higher resistance and worsening compliance causes the ventilator to increase inspiratory pressure to achieve the target volume. The difference between peak plateau pressure can be measured with inspiratory hold just as in volume. Thank you guys.